Section: Introduction. In this section, we focus on the crucial step of placing components in digital hardware design. This placement involves arranging logic gates, standard cells, or larger groups of components, macros, on a 2D chip based on how they are connected in a netlist. The physical layout of these components impacts important metrics like power, area, and performance of the chip. Macro placement, which is our main focus, is particularly critical due to the size and connectivity of macros compared to standard cells. Traditionally, macro placement is done using tools like Innovis from Cadence, which rely on human input and are time-consuming and costly. Using machine learning (ML) techniques for this task shows potential in automating the process and generating better placements than commercial tools that heavily depend on rules. However, existing methods mainly use reinforcement learning (RL), which has limitations such as being inefficient with data and struggling to adapt to new problems. To address these challenges, we take a different approach by using powerful generative models, specifically diffusion models, to create optimal chip placements for different netlists. Diffusion models offer advantages over RL methods as they can be trained efficiently and applied to new netlists without additional training. Our approach leverages advancements in training techniques to achieve improved results. Developing a robust and scalable diffusion model poses its own challenges, such as the limited availability of training data due to the proprietary nature of circuit designs and the large size of circuits with numerous macros and cells. Our proposed neural network model combines graph convolutions and attention layers to be both efficient and effective. We demonstrate through experiments that our model performs well even when applied to new netlists without prior training. We also introduce a method for generating synthetic netlist and placement data easily. By solving the inverse problem of creating a netlist for a given placement, we can generate data without relying on commercial tools or detailed design specifications. This approach enables us to produce placements for netlists without prior training, achieving competitive results on benchmark tests without using realistic circuit data. In summary, our work focuses on improving macro placement in digital hardware design by utilizing generative models and synthetic data generation techniques to overcome the limitations of traditional methods like reinforcement learning. Section Summary. In this section, we introduce the importance of placement in digital hardware design, particularly focusing on the placement of macros due to their size and connectivity. Traditional macro placement methods rely on commercial tools and human input, which can be time-consuming and costly. To address limitations of existing reinforcement learning (RL) approaches, we propose a novel approach using diffusion models that can be trained offline and applied zero-shot to new netlists, resulting in near-optimal chip placements. Our model architecture combines graph convolutions and multi-headed attention layers, and we generate synthetic data to achieve competitive results on benchmarks without training on realistic circuit data. Section: Evaluation Metrics. In this section, we evaluate the placements we generate using two main metrics, legality and half-perimeter wire length, HPWL. Legality measures how suitable a placement is for downstream tasks like routing, while HPWL gives us an idea of the chip's performance. For legality, we check if objects overlap or stay within the canvas bounds. We calculate the legality score by comparing the total area of placed objects within bounds to the sum of individual object areas. A legality score of 1 means all constraints are met. HPWL is crucial as long wires can cause delays between components, affecting timing and power usage. It helps us assess placements before routing. We aim to create legal placements with minimal HPWL. We delve into diffusion models, a type of generative model that uses Langevin dynamics to denoise samples iteratively. Specifically, we focus on the denoising diffusion probabilistic model, DDPM, where we start with Gaussian noise and perform denoising steps to generate the final sample. Each denoising step involves injecting noise and applying a learned denoising model. By training this model to predict added noise, DDPMs can handle complex data distributions effectively. Our model architecture includes GNN and attention layers interleaved to capture both local and distant node information efficiently. We also incorporate MLP blocks between GNN and attention layers to enhance performance without significant computational overhead. Additionally, we use sinusoidal 2D encodings alongside original coordinates to improve object replacement precision. We work with 3 model sizes: small, med, and big, each with varying parameters. Guided sampling is a key feature of diffusion models, allowing us to optimize for objectives like HPWL and legality without extra training. We use universal guidance with potential functions to enhance generated samples. The legality potential considers the distance between objects, while the HPWL potential is simply the wire length. By combining these potentials, we can improve the quality of placements effectively. Section Summary. In this section, we evaluate generated placements using legality and half-perimeter wire length (HPWL) metrics. Legality ensures objects do not overlap and are within canvas bounds, while HPWL approximates chip performance. We aim to create legal placements with minimal HPWL to optimize for downstream tasks like routing. Section: Datasets. In this section, we collect datasets containing pairs of values, x, c, through 2 different methods. For the first method, we create a dataset by using ArtNetGen to generate a netlist, mapping nodes to an ASAP7 PDK, and adding realistic SRAM macros. The Cadence EDA tool then arranges the macros and standard cells concurrently to produce valid and close to optimal placements. To speed up the process, we run netlist generation and placement simultaneously and postpone clock optimization, routing, and power cell placement for later evaluation. Despite taking 15 minutes to generate a sample with around 100 macros and 15K instances, we enhance the dataset by making legal adjustments to the final placements. For the second method, we generate synthetic datasets by randomly placing objects with sizes sampled from a uniform distribution, ensuring legality by checking for overlaps. Following Rent's rule, we assign a number of pins to each object based on a power law. We then create connections between pins by sampling independently for pairs of pins on different objects, with the likelihood of connection decreasing exponentially with the distance between the pins. By adjusting parameters, we produce synthetic datasets with varying wire length optimality. These synthetic circuits allow us to generate around 100K circuits each day, each containing about 200 objects. Our model is evaluated on public benchmark circuits, implemented using PyTorch and PyTorch Geometric, and trained on machines with specific CPU and GPU configurations. The evaluation results on the synthetic datasets show that our model achieves high legality scores and produces placements close to optimal in terms of wire length. By experimenting with different model sizes, we observe improved performance with larger models, indicating the potential for better results with increased model complexity. However, larger circuits pose challenges due to the precision required to place numerous small objects without overlaps, suggesting the need for even larger models to handle such cases. To address this, we propose an unsupervised pre-training approach inspired by LLM training, where we first train on small circuit synthetic data before fine-tuning on larger examples, either synthetic or real. This method shows promising results in improving model performance on larger circuits. Section Summary. In this section, we obtain datasets using 2 methods. One involves generating realistic placements using ArtNetGen and Cadence EDA tools, while the other method creates synthetic datasets by randomly placing objects and connecting them with edges based on a decay function. We then evaluate our model's performance on public benchmarks, pre-train it on small circuit synthetic data, and fine-tune it on larger circuits to achieve legality better than 0.9 and near optimal placements in both realistic and synthetic circuits. Section: Impact of Pre-Training Dataset. In this section, we explored the impact of using different pre-training datasets on our model's performance. When we ran evaluations without any prior training on Synth-L, we discovered that pre-training on the more optimized Synth-M short dataset led to better results in terms of minimizing wire lengths. However, this improvement came at the cost of legality, with Synth-M short performing nearly 10% worse in that aspect. Interestingly, wire length tends to decrease as legality worsens because overlapping objects can reduce wire length more effectively. This suggests that pre-training on datasets with shorter wire lengths may not necessarily produce better models compared to datasets with longer wire lengths. One reason for this could be that in Synth-M short, objects need to be placed much closer together due to a faster decay rate over distance, which can hinder the flow of information within the model's layers. This limitation may result in poorer representations being learned, especially when transferring to other datasets or real circuits with edges between distant objects. Our findings differ from previous work that suggests generating optimal data for object swaps. Additionally, we introduced a guidance method that significantly improved legality and wire length during zero-shot sampling. This guidance not only enhanced the quality of generated samples but also optimized wire length without compromising legality. This approach proved effective without the need for additional training. Our experiments with synthetic datasets demonstrated the potential of diffusion models in addressing complex placement challenges, such as mixed-size placements involving large macros and numerous small standard cells. By clustering standard cells and utilizing a diffusion model, we achieved near-optimal placements for macros and clusters. Our model, pre-trained on Synth-M without fine-tuning but with legality and wire length guidance, showed promising zero-shot transfer to real-world circuits. We also conducted ablations on various components of our model architecture, revealing the critical role of sinusoidal encodings, MLP blocks, and attention layers in achieving high-quality placements. Removing these components led to significant decreases in legality and wire length performance. While our study highlighted the impact of wire lengths and guidance on model performance, there are still areas for further exploration, such as investigating the effects of object size distributions. Additionally, exploring alternative optimization methods like reward-weighted regression or DDPO for fine-tuning the model could be beneficial. The quality of the final optimizer used for mixed-size placements will also play a crucial role in determining the overall placement quality.